The universe would grow old around you, but you would remain frozen, immortal, outpacing time. This changes everything we know about reality. It means distance becomes an illusion, allowing you to cross the entire galaxy in a single heartbeat. We will explore exactly how this cosmic loophole works, why time stops at the speed limit, and reveal what it would actually look like to watch the end of the universe with your own eyes. If you want to see how science rewrote mortality, hit that like button and subscribe, and let me know in the comments, would you risk everything just to live forever? Now settle in, relax, and let the journey begin. The story begins with a problem no one saw coming. For thousands of years, humanity believed time was absolute. A second on Earth was a second on the moon, a second in the depths of space, a second everywhere in the cosmos. Time was the universal clock ticking in the background of reality, unchanging and unstoppable. Then, a 26-year-old patent clerk in Switzerland shattered that belief with a single equation. Albert Einstein revealed that time is not a river flowing at the same speed for everyone. It is an ocean, and your speed through space determines how fast you drift through it. The equation was deceptively simple. Time dilation equals 1 divided by the square root of 1, minus your velocity squared divided by the speed of light squared. But the implications were staggering. Time itself could be bent, stretched, and slowed by motion. For decades, this seemed like abstract mathematics, a curiosity for physicists, not a reality anyone could touch. But in 1971, two scientists named Haffel and Keating decided to test it. They took 4 atomic clocks, the most precise timekeeping devices ever built, and flew them around the world on commercial airliners. One set flew east, one set flew west. When they returned and compared the airborne clocks to identical clocks that stayed on the ground, the results were undeniable. The flying clocks had aged less. Not by much, only a few hundred billionths of a second. But the difference was real and measurable. Time had slowed down for the clocks in motion, exactly as Einstein predicted. The faster you move, the slower time flows for you relative to the stationary world. This effect becomes dramatic as you approach the speed of light. At 10% light speed, roughly 30,000 kilometers per second, time slows by 0.5%. At 50%, it slows by 13%. At 90%, it slows by more than half. And at 99.99%, one day for you equals almost 2 years for everyone else. You are still aging. Your heart still beats. Your cells still divide. But the universe outside is racing forward while you drift through time in slow motion. This is not freezing yourself in ice or stopping your biology. This is bending the fabric of reality itself so that your journey through time happens at a different rate than the rest of existence. Particles from deep space prove this every moment. High in the atmosphere, cosmic rays smash into atoms and create unstable particles called muons. These muons live for only 2 millionths of a second before decaying into other particles. At the speed they travel, they should barely make it 10 kilometers before vanishing. Yet we detect them at sea level, over 60 kilometers down. They survive because they are moving at nearly the speed of light, and time dilation stretches their lifespan. From our perspective, they live longer. From their perspective, if Muons could think, the atmosphere is compressed into a thin shell, and the journey to the ground takes no time at all. Both perspectives are true. Time is relative. Now imagine you are aboard a spacecraft capable of reaching 99% the speed of light. You launch from Earth and accelerate toward a star 100 light-years away. From Earth's perspective, your journey takes just over 100 years. But inside your ship, time flows differently. The trip feels like only 14 years. You step off your ship barely aged, while Earth has spun through a century. Your friends are gone. The cities you knew have been rebuilt. The political borders have shifted. You're a time traveler, not because you bent space-time with exotic matter or wormholes, but simply because you moved fast. This is the gift and curse of relativistic travel. You gain time for yourself, but you lose time with everyone else. You become immortal in the sense that you can cross distances the human lifespan should never allow, but you pay the price of watching your home age into history. Every journey outward is a one-way trip through time. You can return to the place you left, but never to the moment. The discovery arrived in a journal article 18 pages long, published in September 1905, written by a man no one had heard of. Albert Einstein was 26 years old. He worked at the Swiss Patent Office in Bern, evaluating inventions submitted by engineers and tinkerers across Europe. His desk was buried in blueprints for electrical devices, synchronization systems, and machines designed to coordinate the time across distant cities. He spent his days immersed in the mechanics of clocks and signals, but his mind wandered to the architecture of the universe itself. That year, he published 4 papers that would shatter the foundations of physics. One of them changed time forever. The paper was titled On the Electrodynamics of Moving Bodies. It was dense, mathematical, and entirely revolutionary. Einstein began with a simple observation. The laws of physics, he argued, must be the same for anyone moving at constant speed. Whether you are standing still or gliding through space at 1,000 kilometers per second, the rules governing light, energy, and motion do not change. This was the principle of relativity, and it had been known since Galileo. But Einstein took it further. He added a second postulate that seemed impossible. The speed of light in a vacuum is always the same, no matter how fast you're moving when you measure it. A beam of light travels at exactly 299,792,458 meters per second. Whether you're standing still or chasing it at half that speed, this violated common sense. It defied the intuition built from centuries of watching objects move through space. But if both principles were true, something else had to give, and that something was time. Einstein realized that if the speed of light is constant for all observers, then time itself must be flexible. 2 events that appear simultaneous to one observer might occur at different moments for another observer moving at a different speed. Time is not a universal backdrop ticking away the same for everyone. It is woven into the fabric of motion. The faster you move, the slower your clock ticks relative to someone standing still. This was time dilation, and it emerged naturally from the mathematics. Einstein derived a formula that showed exactly how much time slows down as velocity increases. It was elegant, unsettling, and unavoidable. The scientific community did not immediately embrace this idea. It was too strange, too far removed from everyday experience. For decades, physicists had been developing theories to explain why light behaved the way it did, inventing an invisible substance called the ether that filled all of space and carried light waves like water carries ripples. Experiments had failed to detect this ether, but the equations worked. Einstein's approach was different. He eliminated the ether entirely. He said light needed no medium. It simply moved at a constant speed through empty space, and the universe bent itself around that fact. Time dilation was not an illusion, or a quirk of measurement. It was the structure of reality. At first, there was no way to test it. The effect was far too small to detect with the clocks available in 1905. A person moving at the speed of a train or an airplane would age only a fraction of a second slower over an entire lifetime. The difference was real, but invisible. So the theory remained abstract, a mathematical curiosity discussed in academic journals but not proven in the laboratory. Then technology caught up. In 1971, scientists flew atomic clocks around the world and measured the time difference. The clocks that travelled aged less than the clocks that stayed on the ground, exactly as Einstein predicted. In 1977, another experiment measured particles called muons, created by cosmic rays high in the atmosphere. These particles should decay before reaching the ground, but they survived because time slowed down for them as they raced through the air at near light speed. Every test confirmed the same truth: time bends with motion. Einstein never witnessed most of these experiments. He published his paper in 1905 and moved on to other problems, including gravity, which would lead him to an even deeper theory 10 years later. But the foundation he laid that year in Bern, working in a patent office surrounded by blueprints and synchronization devices, became the bedrock of modern physics. He proved that time is not absolute. It flows differently depending on how you move, and if you could move fast enough, you could stretch your seconds into centuries, living a lifetime while the universe aged eons around you. The clock that broke physics was not a device. It was the realization that every clock in the universe ticks at its own pace, and motion determines the rhythm. Time is the dimension through which change happens. It is not a thing you can touch or see, but it governs everything. In physics, time is defined by its measurement. Time is what a clock reads. That sounds circular, but it is precise. We cannot hold time in our hands like we hold a rock, or measure it with a ruler like we measure distance. We can only watch events unfold and count the intervals between them. A heartbeat, a sunrise, the decay of an unstable atom. These are markers, and the spacing between markers is what we call time. For most of human history, time seemed absolute. Newton described it that way in his great work on motion and gravity, published in 1687. He wrote that absolute time flows evenly without regard to anything external, and by another name is called duration. In Newton's universe, time was a river that carried everything downstream at the same speed. A second on Earth was a second on Mars. A second in the past was a second in the future. The flow was universal, unchanging, and the same for every observer in every corner of the cosmos. This matched everyday experience. If you walked across a field or sailed across an ocean, your watch did not slow down. Time ticked forward at the same steady pace no matter what you did or where you went. But Newton's river was an illusion. Time does not flow the same for everyone. It bends. It stretches. It slows down depending on how fast you move and how deep you sink into a gravitational well. Einstein's theory of relativity revealed this truth. Time is not separate from space. The two are woven together into a single fabric called space-time. When you move through space, you alter your path through time. The faster you travel, the slower your clock ticks relative to someone standing still. This is not a trick of perception. It is the structure of reality. Time itself runs at different rates for different observers. To understand this, imagine two identical clocks synchronized to the exact same moment. One stays on the ground, the other flies around the world on an airplane. When the travelling clock returns, it has aged less than the stationary clock. The difference is tiny, only a few billionths of a second, but it is real. The airplane moved through space, and that motion slowed its journey through time. Now scale this effect up. Imagine a spacecraft accelerating to a significant fraction of light speed. The clock aboard that ship would slow dramatically compared to clocks on Earth. At 90% light speed, time aboard the ship flows at less than half the rate of time on the ground. A year for the astronauts becomes more than 2 years for everyone else. This is not science fiction. It is measured, tested, and confirmed every day. Particles called muons are created high in Earth's atmosphere when cosmic rays collide with air molecules. These muons are unstable. They decay into other particles in roughly 2 millionths of a second. At the speeds they travel, they should disintegrate long before reaching the surface, but they do not. They survive the journey because time slows down for them as they race toward the ground at nearly light speed. From the muons' perspective, the atmosphere is compressed and the trip is short. From our perspective on the ground, the muons' clock has slowed and its lifespan has stretched. Both views are correct. Time is relative to the observer. This relativity extends to everything. There is no universal clock ticking away in the background of the cosmos. Every object, every particle, every observer experiences time at their own rate, depending on their motion and their position in space-time. Two events that appear simultaneous to one person might occur at different moments for another person moving at a different speed. The concept of now is not universal, it is local. What you experience as the present moment is not the same present moment for someone else travelling at high velocity relative to you. Your now and their now are different slices through the fabric of space-time. This means time is more like a landscape than a river. In a landscape, you can stand at different elevations. Someone at the top of a mountain experiences a different view than someone in a valley. In space-time, velocity and gravity are like elevation. They determine your rate of passage through time. The faster you move or the deeper you sink into a gravitational field, the slower your clock ticks relative to the rest of the universe. You're not frozen, you're still aging, your neurons are still firing, your heart is still beating. But the universe outside your reference frame is aging faster. Time has not stopped. It has simply diverged. Your seconds and the universe's seconds are no longer synchronized. And if you could reach the speed of light, which is impossible for anything with mass, time for you would stop entirely while the rest of existence raced forward into eternity. The fabric of space and time were bound together long before anyone noticed. For centuries, scientists measured motion through space and tracked intervals through time as if the two existed separately. Distance was one thing, duration was another. You could travel from one place to another without affecting the flow of seconds, or so it seemed. Then, in 1905, Einstein published a paper that fused space and time into a single unified entity. He called it space-time, and the revelation changed physics forever. The breakthrough came from a problem that had been haunting scientists for decades. Light moved at a constant speed, roughly 300,000 kilometers per second, but no one understood why. Every other object in the universe could be accelerated or slowed. A car could speed up. A planet could be captured by gravity and change velocity. But light was different. No matter how fast you moved toward it or away from it, light always travelled at the same speed relative to you. This defied logic. If you chased a beam of light at half its speed, common sense said the light should appear to move away from you at only half speed. But experiments showed otherwise. The light moved away at full speed, as if your motion made no difference at all. Einstein realized the only way this could be true was if space and time themselves adjusted to preserve the constancy of light. When you accelerate through space, time slows down for you. The faster you move, the more dramatically time dilates. This is not an optical illusion. It is not a trick of perception. The universe is structured so that space and time are interwoven, and moving through one affects your passage through the other. You cannot separate them. They're two aspects of the same thing, like width and height on a flat surface. When you tilt the surface, the relationship between width and height changes. When you move through space-time, the relationship between space and time changes. This insight led to a series of predictions that seemed impossible, but turned out to be true. Einstein predicted that a moving clock would tick more slowly than a stationary clock. He predicted that objects moving at high speeds would contract along the direction of motion. He predicted that energy and mass were equivalent, linked by the equation energy equals mass times the speed of light squared. All of these predictions flowed from the same foundation. Space and time are not fixed. They bend and flex in response to motion and gravity. For decades, these ideas remained theoretical. The effects were too small to measure with existing technology. Then, in 1971, two physicists named Joseph Hafele and Richard Keating decided to test time dilation directly. They took 4 atomic clocks, the most precise timekeeping devices humanity had ever built, and synchronized them to the exact same moment. 2 of the clocks stayed on the ground. The other 2 were placed aboard commercial airliners and flown around the world. One set flew east, moving in the same direction as Earth's rotation. The other set flew west, moving against it. When the airborne clocks returned, they were compared to the clocks that stayed on the ground. The results were undeniable. The flying clocks had aged less than the stationary clocks. The difference was tiny, only a few hundred billionths of a second, but it matched Einstein's predictions almost perfectly. The clocks that flew east, moving faster relative to the centre of the Earth, lost more time. The clocks that flew west, moving slower, lost less time. Time itself had bent. Motion through space had altered the flow of duration. The experiment confirmed what Einstein had written 66 years earlier. Time is not absolute. It is flexible, relative, and dependent on velocity. Since then, hundreds of experiments have measured time dilation with ever greater precision. In 2010, scientists used atomic clocks so accurate they could detect time dilation from a height difference of just 33 centimeters. One clock sat on a table, the other was lifted roughly 1 foot higher. The elevated clock ticked faster because it was farther from Earth's gravitational pull. In 2014, researchers at a particle accelerator in Germany pushed lithium ions to 1/3 the speed of light and measured the dilation effect to within a few parts per billion. Every test confirms the same reality. Time flows at different rates depending on where you are and how fast you move. Einstein's revelation was not just a mathematical curiosity, it is the architecture of existence. Space and time are woven together into a single tapestry, and every motion, every acceleration, every journey through the cosmos is also a journey through time at a rate determined by your velocity. You're travelling through space-time right now, moving forward through seconds as surely as you move through meters. And if you could move fast enough, you could change the ratio, trading distance in space for distance in time, stretching your lifespan across centuries while the universe ages millennia around you. Every astronaut who has ever left Earth has travelled through time, not by accident, not by chance. By the simple act of moving faster than the ground beneath them. The effect is small, measured in fractions of a second, but it is real and measurable. Sergei Krikalev holds the human record. He spent 803 days aboard the International Space Station, orbiting Earth at roughly 28,000 kilometers per hour. When he returned to the ground, atomic clocks confirmed what Einstein predicted. Krikalev had aged less than everyone who stayed behind. He travelled roughly 0.02 seconds into the future. This is not theory. This is documented reality. The International Space Station orbits at an altitude where gravity is slightly weaker than it is on the surface, which makes time flow faster. But the station also moves at high velocity, which makes time flow slower. The two effects compete, but velocity wins. Astronauts aboard the station experience time dilation due to their speed, aging microseconds less than people on the ground over the course of months in orbit. The difference is tiny, but the principle is profound. Motion through space alters your passage through time. In 2008, a Buzz Lightyear toy flew aboard the International Space Station for 15 months as part of an educational program. When the toy returned to Earth, it was roughly 0.015 seconds younger than it would have been if it had stayed on the ground. The toy did not age slower because it was frozen or put into stasis. It aged slower because it moved. Time dilation affected every atom in the plastic, every molecule in the paint, every electron in the structure. The toy's clock, if it had one, would have ticked more slowly than clocks on Earth. Not by much. Not enough for a human to notice, but enough to prove the effect is real. The most dramatic demonstration of this phenomenon happens not with astronauts, but with particles created by cosmic rays. High in Earth's atmosphere, roughly 15 to 20 kilometers above the surface, energetic particles from deep space collide with oxygen and nitrogen atoms. These collisions create unstable particles called muons. A muon has a lifespan of approximately 2 millionths of a second before it decays into other particles. At the speeds muons travel, which are close to the speed of light, they should disintegrate long before reaching the ground. The distance is too great. The time is too short. Yet muon detectors at sea level register thousands of these particles every day. The reason they survive is time dilation. From our perspective on the ground, the muons are moving so fast that their internal clocks slow down. Their 2 microsecond lifespan stretches to more than 20 microseconds, giving them enough time to reach the surface before decaying. From the muons' perspective, if particles could think, the journey is different. The atmosphere is compressed by length contraction, another relativistic effect, so the distance to the ground is much shorter. Both views describe the same reality. Time and space adjust depending on your reference frame. This effect is not confined to subatomic particles and astronauts. It shapes the technology you use every day. The global positioning system, which tells your phone where you are on Earth, depends on a network of satellites orbiting at roughly 20,000 kilometers above the surface. These satellites carry atomic clocks synchronized to extraordinary precision. The clocks must be accurate to within billionths of a second because your position is calculated based on how long it takes radio signals to travel from the satellites to your phone. A tiny error in timing translates to a large error in position. But the satellites are moving at roughly 14,000 kilometers per hour, and they orbit in a weaker gravitational field than the surface of Earth. Both factors affect the flow of time. Velocity slows the clocks down. Weaker gravity speeds them up. The gravitational effect is stronger, so the net result is that clocks aboard the satellites tick faster than clocks on the ground. If engineers did not correct for these relativistic effects, the system would accumulate errors of roughly 10 kilometers every single day. Within a week, your navigation system would be useless. Within a month, it would be catastrophically wrong. So every satellite in the network is programmed to adjust its clock to account for time dilation. The system compensates for both the speed of the satellites and their distance from Earth's gravitational pull, ensuring that the clocks aboard the satellites stay synchronized with clocks on the ground. This is not a minor technical detail. It is a continuous real-world application of Einstein's theory of relativity, operating billions of times per day across the planet. Every time you check your location, you're depending on corrections for time dilation. You're relying on the fact that time flows differently in orbit than it does on the surface. In 2010, scientists at the National Institute of Standards and Technology pushed the limits of measurement even further. They used atomic clocks so precise they could detect time dilation from a height difference of just 33 centimetres, roughly 1 foot. One clock sat on a table. The other was lifted slightly higher. The elevated clock ticked faster because it was farther from Earth's centre of mass, experiencing a weaker gravitational pull. The difference was 90 billionths of a second over 79 years, but it was measurable. Even your head ages faster than your feet because it is farther from the ground. The effect is impossibly small, but it is real. Time is not uniform across the length of your body. It is a landscape, and elevation matters. The equation that governs time dilation looks intimidating at first. Time dilation equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. But beneath the symbols lies a simple truth. The faster you move, the slower your clock ticks relative to someone standing still. The relationship is not linear. It curves. It bends. And as you approach the speed of a light, the effect becomes extreme. Start with 0 velocity. You are standing still, or at least moving at the same speed as the earth beneath your feet. Your velocity compared to someone else on the ground is 0. Plug that into the equation and you get one. No time dilation. Your clock and their clock tick at the same rate. This matches everyday experience. You do not age slower when you sit in a chair. Time flows normally because your speed relative to your surroundings is negligible. Now imagine you board a spacecraft and accelerate to 10% the speed of light. That is roughly 30,000 kilometers per second, fast enough to circle Earth in 1.5 seconds. At this speed, time aboard your ship slows by about 0.5%. For every 100 seconds that pass on Earth, 99.5 seconds pass for you. The difference is small but measurable. Over a year, you would age roughly 2 days less than people on the ground. The effect is real, but it is not yet dramatic. Push the speed higher. At 50% light speed, time slows by 13%. For every 100 seconds on Earth, only 87 seconds pass aboard your ship. Over a year, you would age roughly 7 weeks less than the rest of humanity. Now the difference is noticeable. You're not just aging slower, you're experiencing time at a different rate. The universe outside your ship is racing ahead while you drift forward in slow motion. At 90% light speed, the curve steepens sharply. Time aboard your ship slows to less than half the rate of time on Earth. For every 100 seconds on the ground, only 44 seconds pass for you. A year of ship time equals more than 2 years of Earth time. You could travel to a star 20 light years away and experience the journey as roughly 9 years, while 22 years pass on Earth. You step off your ship barely aged, but the world you left has moved a generation into the future. The effect becomes more extreme as you push closer to light speed. At 99%, time slows by a factor of 7. 1 year aboard your ship equals 7 years on Earth. At 99.9%, the factor jumps to 22. 1 year for you is 22 years for everyone else. At 99.99%, the factor reaches 70. A single year of your life equals 70 years of Earth time. You could live a normal human lifespan and watch thousands of years pass outside your window. This is not speculation. The equation has been tested countless times with particles, clocks, and satellites. Every test confirms the same pattern. As velocity increases, time dilation increases. The curve is not a straight line, it is exponential. Small increases in speed near the speed of light produce enormous changes in time dilation. Going from 90% to 99% light speed multiplies the time dilation effect by more than 15 times. Going from 99% to 99.9% multiplies it by another factor of 3. The equation also reveals why nothing with mass can reach the speed of light. As your velocity approaches light speed, the denominator in the equation approaches 0. The time dilation factor approaches infinity. Time aboard your ship would slow to an almost complete stop relative to the universe outside. A single second for you would equal years, centuries, millennia for everyone else, and at exactly the speed of light, time would stop entirely. The journey would be instantaneous from your perspective, but the universe would age infinitely around you. This is impossible. The energy required to reach light speed is also infinite, which is why only massless particles like photons can travel at that speed. But you do not need to reach light speed to experience dramatic time dilation. At 99.999%, just a fraction below the ultimate speed, time slows by a factor of more than 200. 1 year for you equals 2 centuries for Earth. You could cross the galaxy in what feels like a human lifetime, while tens of thousands of years pass outside. This is the gift of relativistic travel. You gain access to distances and timescales that should be impossible for a mortal being. But you pay the price of losing synchronization with the rest of existence. Every journey outward is a leap into the future, and there is no way back to the moment you left. Half the speed of light is 150,000 kilometers per second. At that velocity, you could circle Earth 7 times in a single heartbeat. You could reach the Moon in less than 3 seconds. You could cross from the Sun to Neptune in 8 hours. This speed feels incomprehensible because nothing in human experience comes close. The fastest spacecraft humanity has ever launched, Voyager 1, travels at roughly 17 kilometers per second. Half-light speed is nearly 9,000 times faster than that. But if you could reach it, time itself would change. At 50% the speed of light, time dilation becomes undeniable. For every 100 seconds that pass on Earth, 87 seconds pass aboard your ship. The difference is 13%. This is not a rounding error. This is not a technicality. This is a measurable, experienceable divergence in the flow of time. If you travelled at this speed for 1 year by your clock, 1 year and 2 months would pass on Earth. You would age 12 months. The rest of humanity would age 14 months. You would return home having experienced less time than the people who stayed behind. The numbers become more dramatic the farther you travel. Imagine a journey to Proxima Centauri, the nearest star system outside our own, roughly 4 light-years away. At half-light speed, the trip would take 8 years from Earth's perspective. But aboard your ship, time flows slower. The journey would feel like roughly 7 years. You would step off your ship having aged 7 years while 8 years passed on Earth. The difference is not enormous, but it is real. You would be 1 year younger than you should be if time flowed the same for everyone. Now imagine a longer journey. Alpha Centauri is part of a triple-star system that includes Proxima Centauri. If you travelled there and back at half-light speed, the round trip would take 16 years from Earth's perspective. But aboard your ship, the journey would feel like roughly 14 years. You would age 14 years. Your friends and family on Earth would age 16. You would return 2 years younger than expected. People born on the day you left would be 2 years older than you remember. Children would have grown taller. Adults would have aged further. The world would have moved forward while you drifted through time at a different rate. This effect scales with distance. A journey to a star 10 light-years away and back would take 40 years from Earth's perspective at half-light speed. But you would experience only 35 years. You would step off your ship having aged a normal human span, but the Earth would be 5 years ahead. A journey to a star 50 light-years away would take 200 years from Earth's perspective. You would experience 174 years. Everyone you knew would be long dead. Entire generations would have been born, lived and passed away while you travelled. You would return to a world you do not recognise, populated by people who know you only from history. But half-light speed is just the beginning. The time dilation curve steepens dramatically as you approach the speed of light. The difference between 50% and 90% light speed is not just a matter of going faster. It is a transformation in how time itself behaves. At 90%, time aboard your ship slows to less than half the rate of time on Earth. For every 100 seconds on the ground, only 44 seconds pass for you. The journey to Proxima Centauri would take roughly 4.5 years from Earth's perspective, but you would experience only 2 years. The round trip would be 9 years for Earth and 4 years for you. You would return 5 years younger than expected. The technology required to reach half-light speed does not exist. The energy demands are staggering. The engineering challenges are immense. Accelerating a single kilogram of mass to half-light speed requires roughly 1.1 times 10 to the power of 16 joules of energy, equivalent to the total energy output of the United States for several days. Accelerating a spacecraft large enough to carry humans, supplies, and equipment would require energy on the scale of entire nations consuming power for years. And that is just to accelerate. You would need the same amount of energy again to slow down at your destination, and twice that to return home. But the principle is sound. Time dilation at half-light speed is not speculation. It is physics, tested and confirmed with particles, clocks, and satellites. Every muon that survives its journey through the atmosphere proves the effect. Every atomic clock flown on an airplane confirms it. Every satellite in the navigation system accounts for it. If humanity ever develops the technology to reach relativistic speeds, time dilation will not be a surprise. It will be the expected consequence of motion through space-time, and the faster we go, the more dramatic the effect becomes, until velocity transforms us into travellers not just through space, but through time itself. Time is not universal. There is no cosmic clock ticking away in the background of the universe, no shared moment called now that everyone experiences together. What you call the present moment is different from what someone else moving at a different velocity calls the present moment. Your now and their now are not synchronized. They are offset, shifted, separated by the structure of space-time itself. This is one of the strangest consequences of relativity, and one of the hardest to accept. But it is true. Imagine two spacecraft passing each other in deep space. One is yours, the other belongs to another traveller moving at half the speed of light relative to you. At the moment you pass, you both set your clocks to 0 and agree that this instant is now. But immediately after you separate, your definitions of now begin to diverge. Events that appear simultaneous to you do not appear simultaneous to the other traveller. A supernova exploding in a distant galaxy might happen in your present moment, but from the perspective of the other traveller, that same explosion occurs in their past or their future, depending on the direction they are moving. This is not an illusion. It is not a trick of perception. The fabric of space-time itself is structured so that simultaneity is relative. Two events separated by distance do not have a universal order in time unless one event causes the other. If you send a light signal from Earth to Mars, the signal's departure happens before its arrival for every observer in the universe. Cause precedes effect. But for events that cannot influence each other because they are separated by distances light cannot cross in time, there is no universal agreement on which event happens first. This becomes even more disorienting when you consider motion. If you are travelling toward a distant star at 90% the speed of light, events happening at that star right now in your reference frame occurred years ago, in the reference frame of someone standing still relative to the star. Your now extends into their future. Conversely, if you are travelling away from the star, your now reaches into their past. The faster you move, the more dramatically your present moment diverges from the present moment of stationary observers. To understand this, imagine a line representing all of space at a single instant in time. For someone standing still, this line is horizontal, cutting through space-time at a specific moment. Every event on that line is happening now for that observer. But for someone moving at high velocity, the line tilts. There now is a different slice through space-time, angled relative to the stationary observer's slice. Events that lie on one person's line of simultaneity do not lie on the other person's line. What is happening right now for one observer is in the past or future for the other. This has profound implications for anyone travelling at relativistic speeds. If you accelerate toward a distant star, that star's timeline rushes forward from your perspective. Years pass there in what feels like moments to you, not because time is speeding up at the star, but because your motion through space-time has changed what you call now. The faster you go, the more the star's future becomes your present. By the time you arrive, decades or centuries may have passed at the star, while only years passed for you aboard the ship. You have not travelled faster than light. You have simply moved through space-time in a way that shifted your timeline relative to the star's timeline. The reverse is also true. If you turn around and accelerate back toward Earth, Earth's timeline rushes forward from your perspective. The years you spent travelling away are compounded by the years that passed during your return journey. When you arrive home, more time has passed on Earth than you experienced. Your family has aged, your friends have grown old. The world has moved into the future while you drifted through time at a different rate. This is the twin paradox, and it is not a paradox at all. It is the inevitable consequence of relativity. The concept of now is local. It applies to your immediate surroundings, to the objects and events you can interact with in real time, but it does not extend across the universe in a meaningful way. The present moment on a star 100 light-years away is not defined. It depends on your motion. If you're standing still, the star's now might align with your now in a certain reference frame. But if you start moving, the alignment shifts. The star's present moment moves into your past or future depending on the direction and speed of your motion. There is no absolute synchronization. There is only your reference frame and the consequences of your velocity through space-time, And if you move fast enough, you can step outside the normal flow of time entirely, watching the universe age around you, while you remain locked in your own slower rhythm, untethered from the shared experience of existence. The closer you get to the speed of light, the stranger the universe becomes. Time does not slow down in a steady, predictable way. It collapses. The time dilation effect is gentle at low speeds, barely noticeable at 10 or 20% light speed. But as you push past 90%, the curve steepens into a wall. Every additional fraction of a percent demands exponentially more energy and produces exponentially greater time dilation. You're not climbing a hill. You're approaching a vertical cliff that extends infinitely upward. At 99% light speed, time aboard your ship flows at roughly 1/7 the rate of time on Earth. 1 year for you equals 7 years for everyone else. This is already dramatic, but the curve has only just begun to steepen. Push to 99.9% and the factor jumps to 22. 1 year for you equals 22 years on Earth. Add another 9 and reach 99.99%. Now the factor is 70. 1 year aboard your ship equals 70 years on the ground. The universe outside your window is aging at a speed that feels impossible, but from your perspective inside the ship, time flows normally. Your heart beats at the same rhythm. Your thoughts unfold at the same pace. It is the rest of existence that has accelerated into a blur. At 99.999%, the dilation factor exceeds 200. 1 year for you equals more than 2 centuries for Earth. You could live a normal human lifespan aboard the ship, 80 or 90 years, and return to find that 16,000 years have passed on Earth. Everyone you knew would be dust. Civilizations would have risen and fallen. Languages would have evolved beyond recognition. The continents themselves would have shifted. You would step off your ship into a world that remembers you only as a legend, if at all. But you still have not reached the barrier. Add more 9s. At 99.9999% light speed, time dilation exceeds 700. 1 year aboard your ship equals 7 centuries on Earth. At this speed, a journey across the Milky Way, 100,000 light years from edge to edge, would take roughly 100,000 years from Earth's perspective. But aboard your ship, the journey would feel like only 140 years. You could cross the entire galaxy in what feels like a long human lifespan. You would age naturally, watching the stars drift past your window while millennia accumulated outside. The energy required to reach these speeds grows without bound. Accelerating a single kilogram of mass to 99.9999% light speed requires roughly 7 times 10 to the power of 17 joules, equivalent to the total energy output of the entire United States for months, and that energy accelerates only 1 kilogram. A spacecraft capable of carrying humans, supplies, life support, and propulsion systems would mass thousands or tens of thousands of kilograms. The energy demand scales proportionally. You would need the power output of nations, perhaps the combined energy of entire planets, just to accelerate a single ship to near light speed. And even then, you face another problem. As your velocity increases, your mass increases from the perspective of a stationary observer. This is relativistic mass, another consequence of motion through space-time. The faster you go, the heavier you become, and the more energy is required to accelerate you further. At 99% light speed, your mass has increased by a factor of 7. At 99.9%, the factor is 22. At 99.99%, it is 70. The ship that started with a rest mass of 10,000 kilograms now has an effective mass of 700,000 kilograms from the perspective of someone on Earth. This creates a feedback loop. The more energy you add, the faster you go. But the faster you go, the more massive you become, and the more energy is required to accelerate further. As you approach light speed, the energy required approaches infinity. You can never reach it. The barrier is absolute. No amount of fuel, no matter how advanced your propulsion system, can push an object with mass to exactly the speed of light. You can get closer and closer, adding 9s to the decimal, but you will always fall short. The universe does not allow it. This is not a technological limitation. It is not a problem waiting for a better engine or a more efficient reactor. It is the structure of space-time itself. Light speed is not a speed limit in the conventional sense, like a highway sign telling you to slow down. It is a boundary built into the fabric of reality. Only massless particles, photons, and perhaps gravitons can travel at exactly that speed. Anything with mass is forever locked below the barrier, able to approach but never touch, always asymptoting toward infinity without ever arriving. And as you approach, time itself warps around you, slowing to a crawl while the universe outside races forward, transforming you into a traveller adrift between moments, watching eternity unfold in the blink of an eye. The speed of light is not a speed limit. It is a boundary in space-time itself. No object with mass can reach it, no matter how much energy you pour into acceleration. The reason is not technological, it is fundamental. As your velocity increases, your mass increases from the perspective of a stationary observer. The faster you go, the heavier you become, and the heavier you become, the more energy is required to accelerate further. This creates a feedback loop that approaches infinity as you approach light speed. At rest, an object has what physicists call rest mass. This is the intrinsic mass of the object, the mass it would have if it were not moving, but motion adds energy, and energy has mass. The faster you move, the more kinetic energy you carry, and the more massive you become from the perspective of someone standing still. At low speeds, this effect is negligible. A car driving down a highway gains mass, but the increase is so small it cannot be detected. But at relativistic speeds, the effect becomes enormous. At 90% light speed, your mass is increased by a factor of roughly 2.3. A spacecraft with a rest mass of 10,000 kilograms now has an effective mass of 23,000 kilograms from the perspective of Earth. This does not mean the ship has gained atoms. The number of particles aboard the ship has not changed. But the energy of motion has added to the total mass energy of the system, and because mass and energy are equivalent, that added energy appears as added mass. At 99% light speed, the factor jumps to 7. The 10,000 kilogram ship now has an effective mass of 70,000 kilograms. At 99.9%, the factor is 22. The ship's mass has grown to 220,000 kilograms, and this mass increase affects everything. It affects the gravitational pull the ship exerts on nearby objects. It affects the amount of force required to change the ship's trajectory. Most importantly, it affects the amount of energy required to accelerate the ship faster. As you push closer to light speed, the mass grows without bound. At 99.99%, the mass factor is 70. At 99.999%, it exceeds 200. Add more nines and the factor climbs into the thousands, then millions, then billions. The curve is exponential. It approaches infinity as velocity approaches light speed. To push an object with mass to exactly the speed of light would require infinite energy, and infinite energy does not exist. The total energy content of the universe is finite. You cannot gather enough fuel, enough power, enough force to break through the barrier. This is why only massless particles can travel at light speed. Photons, the particles of light, have no rest mass. They are pure energy, and they move at exactly the speed of light from the moment they are created. They cannot be slowed down, they cannot be accelerated, they exist only at light speed. If a photon ever stopped moving, it would cease to exist. The same is true for gravitons if they exist, and possibly for gluons in certain conditions. These particles have no mass, so they are not subject to the feedback loop that traps everything else below the light speed barrier. Some physicists have speculated about particles that move faster than light. These hypothetical particles are called tachyons, and they exist in a strange mirror world where the rules of relativity are inverted. In our world, particles with mass move slower than light, and it takes infinite energy to reach light speed. In the tachyon world, particles move faster than light, and it would take infinite energy to slow down to light speed. The barrier works in reverse, but tachyons have never been detected. There is no evidence they exist, and even if they did, they could not be used for faster than light travel, because crossing the barrier from below light speed to above light speed is still impossible. Other proposals involve bending space-time itself. The Alcubierre drive, proposed in 1994, describes a theoretical method of compressing space in front of a spacecraft and expanding space behind it, creating a bubble that moves faster than light while the ship inside remains stationary relative to the bubble. The ship does not move through space. The bubble moves through space, carrying the ship with it. Because space-time itself can expand or contract at any speed, the bubble is not bound by the light speed limit. But this scheme requires vast amounts of negative energy, a substance that may not exist. And even if it could be built, some research suggests the drive would be unstable and collapse under quantum effects. Wormholes offer another theoretical bypass. A wormhole is a tunnel through space-time connecting two distant points. If you could create and stabilize a wormhole, you could step through one end and emerge at the other without traveling the distance in between. This does not violate the light speed limit because you're not moving faster than light through space. You're taking a shortcut through space-time itself. But wormholes also require exotic matter to keep them open, and there is no evidence such matter exists. Every known form of matter collapses a wormhole the moment it forms. The light speed barrier is absolute for objects moving through space. You can approach it. You can get closer and closer, adding nines to the decimal until the energy requirements exceed the output of stars. But you will never reach it, and you will never cross it. The wall is built into the structure of reality, woven into the equations that govern motion, time, and energy. It is not a failure of engineering. It is the price of existence in this universe, where mass and light speed are incompatible, and the only way to touch infinity is to have no mass at all. A photon experiences no time. From the moment it is born until the moment it is absorbed, no time passes from the photon's perspective. It could travel for 1 second or 13 billion years. It could cross a room or span the observable universe. To the photon, the journey is instantaneous. It departs and arrives in the same moment. This is not poetic language. This is the mathematics of relativity applied to a particle moving at exactly the speed of light. Time dilation increases as velocity increases. At 90% light speed, time slows to less than half. At 99%, it slows to 1/7. At 99.9%, it slows to 1/22. The curve steepens exponentially as you approach light speed. And at exactly light speed, the time dilation factor becomes infinite. Time stops completely. Not slows, stops. From the reference frame of a photon, if such a frame could be meaningfully defined, the entire history of the universe from beginning to end happens in zero time. This has profound implications. A photon emitted from a distant galaxy 13 billion years ago has been travelling through space for nearly the entire age of the universe from our perspective. We see that photon as ancient, a relic from the early cosmos. But from the photon's perspective, no time has passed. It was created and absorbed in the same instant. The journey that took 13 billion years to us took zero time to it. The photon does not age. It does not decay. It does not experience duration. It exists only in a single frozen moment that spans the cosmos. Length contraction mirrors this effect. Just as time slows with velocity, distances shrink. At 90% light speed, distances contract to less than half their rest length along the direction of motion. At 99%, they contract to 1/7. At light speed, distances collapse to zero. From a photon's perspective, the entire universe in the direction of travel is compressed into a single point. There is no distance to cross. The source and the destination occupy the same location in space. The photon is simultaneously everywhere and nowhere along its path. This is why photons cannot be slowed down or stopped without being absorbed. A photon moving through empty space always travels at exactly light speed. It has no rest frame. It cannot exist at any other velocity. If you could somehow reduce a photon's speed, even slightly, it would cease to be a photon. It would transform into something else or vanish entirely. Massless particles exist only at the boundary, moving at the one speed the universe forbids everything else from reaching. Quantum entanglement does not change this. Entangled particles are connected in a way that seems to violate the light speed limit. When you measure one particle, the state of the other particle is instantly determined, no matter how far apart they are. This correlation appears to happen faster than light, but no information is transmitted. You cannot use entanglement to send a message. The measurement results are random from the perspective of each observer. Only when you compare the results later, using conventional slower-than-light communication, do you see the correlation. Einstein called this spooky action at a distance, and it troubled him deeply. He believed it suggested quantum mechanics was incomplete, that some hidden variable must be coordinating the particles without requiring faster-than-light influence. But decades of experiments have confirmed that entanglement is real, and there are no hidden variables. The particles are genuinely connected in a way that defies classical intuition. Yet this connection cannot be used to transmit information faster than light. The reason is subtle. When you measure an entangled particle, you get a random result. Spin up or spin down. Polarization horizontal or vertical. The outcome is unpredictable. Your partner on the other side of the galaxy, measuring their entangled particle, also gets a random result. Neither of you can control the outcome. You cannot force your particle into a specific state to encode a message. Any attempt to do so breaks the entanglement. The particles become independent and the correlation vanishes. Only after you reunite and compare your measurement results do you discover the correlation. Your random sequence of results is perfectly anti-correlated with their random sequence. When you measured spin up, they measured spin down. When you measured horizontal, they measured vertical. But this information is useless for communication. You both have random data. The correlation proves entanglement existed, but it reveals nothing until you compare notes using conventional, slower-than-light methods like radio signals or physical meetings. So the light-speed barrier remains intact. Entanglement is strange, counterintuitive, and powerful for certain quantum technologies like cryptography and computing. But it does not allow faster-than-light communication. Information still travels at light speed or slower. And photons, the carriers of light itself, still experience zero time as they cross the universe, locked forever at the boundary where time stops and distance vanishes, alone in a single eternal instant that contains the entirety of their existence. Two twins stand together on Earth. One boards a spacecraft, the other stays behind. The spacecraft accelerates to 90% the speed of light and travels to a star 10 light-years away, then turns around and returns home. From Earth's perspective, the journey takes roughly 22 years, 10 years to reach the star at 90% light speed, plus a brief period of deceleration and turnaround, plus 10 years to return. But aboard the spacecraft, time flows more slowly. The travelling twin experiences only about 9.5 years. When the twins reunite, the traveller is younger, not by perception, not by feeling. Younger by measurable biological age. Fewer cells have divided, fewer heartbeats have passed, less time has elapsed. This is the twin paradox, and it is not a paradox at all. It is a direct consequence of time dilation, confirmed by every test of relativity. The asymmetry arises because the twins do not experience the same journey through space-time. The Earth-bound twin remains in a single inertial reference frame, moving at constant velocity relative to the distant stars. The travelling twin accelerates, travels at high speed, decelerates, turns around, accelerates again, and decelerates once more upon return. The travelling twin changes reference frames multiple times. This acceleration breaks the symmetry between the two perspectives. Some argue that motion is relative, so each twin should see the other as moving, and each should age more slowly from the other's perspective. This seems to create a contradiction. How can both twins be younger than the other? The resolution lies in acceleration. The Earth-bound twin does not accelerate. The travelling twin does. Acceleration is not relative. It is absolute. You can feel acceleration. You cannot feel constant velocity. When the spacecraft fires its engines and accelerates, the twin aboard feels the force. The twin on Earth feels nothing. This difference is detectable by any observer in the universe, and it is the difference that resolves the paradox. The effect has been measured countless times. In 1971, atomic clocks were flown around the world on commercial airliners. When they returned, they had aged less than identical clocks left on the ground. In 2010, atomic clocks were raised by just 33 centimeters, and the elevated clocks ticked faster due to weaker gravity. Astronauts aboard the International Space Station age microseconds less than people on the ground over the course of months. Every test confirms the same reality. The twin who travels at high velocity ages less than the twin who stays home. The paradox becomes more dramatic at higher speeds. Imagine the travelling twin accelerates to 99% light speed instead of 90%. The journey to the same star 10 light-years away now takes roughly 10 years from Earth's perspective, plus 10 years to return, for a total of about 20 years. But aboard the spacecraft, time flows at roughly 1/7 the normal rate. The travelling twin experiences only about 3 years. When the twins reunite, the traveller is 17 years younger. The Earth-bound twin has aged from 30 to 50. The traveller has aged from 30 to 33. Push the speed higher still. At 99.9% light speed, the time dilation factor jumps to 22. A 20-year journey from Earth's perspective becomes less than 1 year for the traveller. The twins meet again after 2 decades, but the traveller has aged only 10 months. The Earthbound twin is 50 years old. The traveller is 30 years and 10 months. The difference is more than a generation. At 99.99%, the effect is surreal. The same journey that takes 20 years from Earth's perspective takes less than 4 months for the traveller. The Earthbound twin ages 2 decades. The traveller ages 1 season. They are no longer peers, they are separated by time itself, living through the same events at wildly different rates. The traveller steps off the ship into a future where friends have married, children have been born, careers have ended, and the world has moved on. This is not science fiction. This is relativity tested and proven. The twin paradox is a thought experiment, but the physics is real. If humanity ever builds spacecraft capable of reaching relativistic speeds, travellers will age more slowly than the people they leave behind. Every journey will be a leap into the future. You could visit a distant star and return to find that decades or centuries have passed on Earth while you experienced only years. You would be a time traveller, moving forward through the timeline at a different rate than the rest of humanity, watching history unfold in fast-forward from the window of your ship. The paradox is not that this seems impossible. The paradox is that it is inevitable, built into the fabric of space-time, waiting for anyone brave or reckless enough to move fast enough to feel it. Every second, thousands of particles rain down from the sky and pass through your body. They are called muons, and they are created roughly 15 kilometers above the surface when cosmic rays from deep space collide with atoms in the upper atmosphere. These collisions shatter atomic nuclei and produce showers of unstable particles, including muons. A muon is essentially a heavy electron. It has the same electric charge, but it is 200 times more massive, and it is unstable. Left alone, a muon decays into lighter particles in approximately 2 millionths of a second. This creates a problem. Muons are created high in the atmosphere and travel toward the ground at close to the speed of light, roughly 99.9%. At that speed, they cover about 300 meters per microsecond. In their brief lifespan of 2 microseconds, they should travel no more than 600 meters before decaying. But they are created 15 kilometers up, which is 15,000 meters. Even moving at near light speed, they should disintegrate long before reaching the surface. They should vanish in the upper atmosphere, invisible to detectors on the ground. Yet Muon detectors at sea level register thousands of these particles every day. They survive the journey. They reach the ground intact and pass through buildings, mountains, and human bodies before finally decaying or being absorbed. This should be impossible if Newtonian physics were correct. But relativity explains it perfectly. The muons survive because time itself is running slower for them. From our perspective on the ground, the muons are moving at 99.9% the speed of light. At this velocity, time dilation stretches their lifespan by a factor of roughly 22. Instead of living for 2 microseconds, they live for 44 microseconds from our perspective. This is enough time to cover 15 kilometers and reach the surface. The muons do not live longer because something has changed inside them. They live longer because time flows more slowly for objects moving at relativistic speeds. But there is another way to view this. From the muon's perspective, time flows normally. The muon's internal clock ticks at the usual rate, and it still decays after 2 microseconds of its own time. But from the muon's reference frame, the atmosphere is not 15 kilometers thick. It is compressed by length contraction, another relativistic effect. At 99.9% light speed, distances along the direction of motion shrink by a factor of 22. The 15-kilometer atmosphere becomes less than 700 meters thick from the muon's perspective. The muon travels this shorter distance in 2 microseconds and reaches the ground before decaying. Both perspectives describe the same reality. This is not theory. Muons are detected constantly. Their survival is measured, counted and analysed in particle physics experiments around the world. The agreement between the observed muon flux at sea level and the predictions of relativity is precise. If time dilation did not exist, the flux would be thousands of times lower. Almost no muons would survive the journey, but they do survive in exactly the numbers relativity predicts, proving that time bends with motion. Scientists have even measured this effect directly by comparing muon decay rates at different altitudes. Detectors placed on mountaintops register more muons than detectors at sea level, as expected. The difference matches the predictions of time dilation. Muons created high in the atmosphere have more time to decay as they descend, and fewer survive to reach lower altitudes. But the survival rate is higher than Newtonian physics would allow because time dilation extends their effective lifespan. This is one of the cleanest, most direct proofs of time dilation available. Muons are natural clocks. They tick at a fixed rate determined by quantum mechanics, and they stop ticking when they decay. By measuring how many reach the ground and comparing that to how many should reach the ground, without time dilation, physicists can confirm that time flows differently for objects in motion. The muons are unwitting time travelers, aging more slowly than the Earth beneath them as they race toward the surface at near light speed. And every muon that reaches the ground is evidence that time is not absolute, not universal, not the same for everyone. It is flexible, relative, and dependent on velocity. Every particle that survives the journey from the upper atmosphere to sea level is proof that Einstein was right, and that motion through space alters your passage through time in ways that can be measured, tested, and observed every single day above your head. Slip inside the hull of a ship built for the edge of light speed. This vessel is not just a machine, it is a time capsule, gliding through space-time at such velocity that every second inside stretches into hours, years, or centuries outside. If you were a crew member, the clocks on the wall would seem ordinary to you. Your heartbeat would be unchanged. Your conversations, your meals, the small daily rituals of existence, all would unfold in their normal rhythm. Yet, outside your windows, the cosmos would age and change at a rate so astonishing it would blur the boundaries of past, present, and future. As you approach 99.9%, the speed of light, relativistic time dilation becomes your silent companion, smoothing out the bumps and stutters of human perception into a river of slow, tranquil moments. For every month you live aboard the ship, nearly 2 years pass everywhere else. If your mission lasted a decade from your perspective, you would return to find entire generations gone, cities rebuilt, and the starlit map completely rearranged by the patient hand of astronomical time. The journey itself would challenge your senses. The stars ahead would shift and pile up into a brilliant blue glow, compressed by the relentless advance of your velocity. Behind you, the night would darken and recede, stretched into longer and longer waves until the galaxies seemed to slip away, invisible to human sight. Space would flatten along your trajectory, contracted like a drawn bowstring. The journey to a star 50 light-years away, which should have required half a century even at light speed, would unfold in a fraction of that time for you. The universe stretches for everyone else, but shrinks for you, the voyager. Yet, no technology can wash away the dissonance waiting at your destination. Whatever world you reach will not be the one you left. The calendar on their walls runs far ahead of yours. History has bloomed and withered in your absence. You have lived a normal life, but outside. Centuries have passed. You have become a visitor from the distant past, a living fossil of your own era, standing on new ground as both ancestor and explorer. This is not science fiction. It is proven, confirmed with particles called muons that survive far longer than they should, because they are born flying close to the speed of light. It is measured with atomic clocks on jets and satellites, with data from the GPS network correcting for the difference that gravity and velocity impose. These are the echoes of relativity, showing us that a starship racing through space does more than travel. It warps the very meaning of time for those within and for those left behind. So what's it like inside a ship racing through billions of years in the blink of an eye? It is ordinary life, sheltered by the most extraordinary phenomenon the universe has to offer. It is dinner with friends, the slow comfort of sleep, the memory of Earth fresh in your mind even as that Earth fades into legend behind you. The life of every astronaut, every voyager, compressed and preserved, a capsule of the present drifting through the river of the future. For those aboard, time remains a gentle current. For everyone else, your journey is an arrow that pierces right through the long, patient heart of history. Imagine looking out the window of that light-speed starship. The stars ahead would squeeze into a dazzling tunnel of bright blues and whites. Because of relativistic aberration, the light from stars in front of you compresses into a smaller, brighter patch of the sky. The familiar constellation you once knew would be distorted and shifted, transformed into a brilliant panorama of compressed light. Colours change, too. Light that once appeared yellow or red shifts into bluer wavelengths, approaching the ultraviolet, painting the stars in hues invisible to the naked eye. Behind you, the night sky fades into darkness. Light from stars behind stretches into longer, redder wavelengths, some slipping out of the visible spectrum altogether. This is the Doppler effect in its most extreme form. The wavelengths of light are compressed ahead and stretched behind, altering the very colours of space itself. The static, eternal canvas of stars you remember has become a dynamic, shifting spectacle. Space itself contracts. This is length contraction, one half of the time-space duo unveiled by Einstein. Distances along your direction of motion shrink. A star 10 light-years away contracts to just a few light-years from your perspective. The vast emptiness of space compresses, making distant galaxies feel surprisingly near. The journey that should span decades shrinks to mere years inside the ship. Everything outside your window is warped. Space bends, light distorts, and time stretches differently for you than for those left behind. These effects would not just be visual curiosities, they would influence navigation, communication, and survival. Instruments designed to measure distance, speed, and direction would need constant recalibration to account for shifting light and contracted space. Sensors and cameras would capture warped images. Your navigational maps, drawn with earthbound geometry in mind, would require rewriting with relativistic formulas to stay accurate. Yet, within the ship, time would flow normally. Your clock ticks, your heart beats, and your mind thinks in a steady rhythm. The warping of light and space outside is spectacular, but inside the ship life is calm. The ship is both a sanctuary and a gateway, preserving your time even as it stretches the cosmos around you into an abyss of distortion and wonder. This vision of the universe through your window is not guesswork or fantasy. It springs from equations tested and confirmed in particle accelerators, atomic clocks, and satellite systems. It is the universe seen through the lens of relativity, strange, beautiful, and utterly different from the steady, unchanging world we know. Travelling near light speed transforms space and time into a fluid, changing mosaic, turning the cosmos into a shifting landscape that stretches, contracts, and shines with unimaginable colours. Every star becomes a beacon, every journey a voyage through a kaleidoscope of space and time. You're not just moving through the universe, you're living inside its secret machinery, watching it transform, warp, and dance around you as you cross the gulf between stars and centuries. The window of your ship frames a universe both alien and awe-inspiring, a place where the familiar is melted into the extraordinary, and where the simple act of moving fast opens the door to a world of wonder beyond imagination. Imagine setting a course to cross the Milky Way, a vast ocean of stars spanning 100,000 light-years from edge to edge. To us on Earth, that distance is staggering. Light itself takes 100,000 years to cross it, and our fastest spacecraft would take millions of years. But aboard a ship built for relativistic speeds, the journey transforms completely. At 99.99% the speed of light, the galaxy's span contracts to less than 2,000 light-years from your perspective. Time stretches, space shrinks, and the unthinkable becomes possible within a human lifetime. A journey that looks like 100,000 years to distant observers becomes less than 2 decades for you. You set off on a voyage of a lifetime, decades in your own frame, centuries in the galaxy's frame. You watch stars whiz past like raindrops on your window, all the while living your normal years inside the ship's calm sanctuary. But this gift is bittersweet. While centuries pass elsewhere, your loved one's age and the world you once knew slips into the realm of history. When you return, your friends are ancestors, their faces familiar only from portraits and stories. You have travelled not just across space, but forward in time, making you both an explorer and a time traveller. Navigating such a journey demands more than charts and fuel. The relativistic effects warp signals and the apparent positions of stars around you. Doppler shifts change colours. Relativistic aberration bends light paths. Navigation systems must be built to see the universe as you do, a shifting, compressed, energetic panorama distorted by your speed. New navigation methods harness these relativistic cues, creating maps in motion that guide your starship safely through the cosmic ocean. This is the paradox and wonder of relativistic travel. Space and time are no longer distant abstractions, but variables in your daily voyage. The galaxy folds before you, millennia pass behind you. You journey across a living, breathing universe where relativity is not theory. It is home. Embarking on a journey near the speed of light offers the gift of time itself, an elongated lifespan allowing you to cross vast cosmic distances in what feels like a human lifetime. Yet, this blessing comes with profound sacrifices. Every second you live aboard your relativistic starship is a second lost to those you left behind. While your heart beats steadily, civilizations rise and fall outside your window. Friends grow old, families evolve, and the world you knew becomes a memory. Communication becomes a battlefield of delays and distortions. The speed of light limits all messages, no matter how advanced your technology, to finite speeds. As your velocity approaches light speed, signals between you and Earth stretch and skew. Time dilation slows your clock relative to Earth, while Doppler shifts color your transmissions across the electromagnetic spectrum, shifting radio waves into optical or infrared, or stretching them beyond detection. Messages take years or decades to travel back and forth, making real-time conversation impossible. This isolation imposes a psychological toll. Astronauts on long missions rely on constant contact with home for emotional support. At relativistic speeds, this connection frays, threatening loneliness and dislocation, being physically present in space but emotionally adrift in time. The starship becomes both sanctuary and prison, a vessel where you live in normal time while the universe spins centuries ahead. Moreover, navigation and control become autonomous necessities. The delays in command signals mean that onboard computers and artificial intelligence must handle many decisions. Pilots become overseers of AI systems rather than hands-on controllers. The ship's autonomy protects the crew but deepens separation. You are a captain, yes, but one set adrift amid the galloping river of cosmic time. Finally, the technology and energy required to accelerate to near-light speed are staggering. Hundreds of times more energy is needed to approach the speed of light than to achieve today's fastest spacecraft velocities. Propulsion systems capable of such feats lie in the realm of future science and engineering, demanding breakthroughs in physics, materials, and energy production. The cost is not just energy, but profound changes to the biology, psychology, and social life of those who embark. This is the true price of immortality. To live long, you must sacrifice the time and companionship of those you love. Immortal in years, but isolated across centuries, forever travelers stepping lightly through an age their peers never see. The gift is vast, but so is the loss, a solitary odyssey through a universe where time itself bends, leaving you a stranger in a future that has already passed. If speed bends time, then gravity bends it even more. Black holes, cosmic wells of unimaginable mass, twist time into profound depths. Falling toward one is like descending an impossible staircase where every step stretches moments into eternities. Near a black hole, gravity grows so strong that it warps space-time to extraordinary degrees. Time, which ticked normally aboard your starship at 99% light speed, slows to a crawl. To an outside observer far from the black hole, someone near its edge, the event horizon, appears frozen, trapped in an eternal moment. Their clock slows, heartbeats lengthen, words seem to draw out into endless echoes. This is gravitational time dilation, the bending of time by mass. The greater the gravity, the slower time flows relative to distant observers. While astronauts racing to distant stars face relativistic time dilation from velocity, those falling into black holes face an even more extreme effect caused by gravity itself. Imagine observing a friend approaching a black hole's event horizon. They descend toward the abyss, moving slower and slower from your perspective. They never seem to cross the horizon, frozen in a thin slice of time. For them, however, time passes normally. They cross the boundary, but everything beyond lies hidden in an obscured future, inaccessible to you. One of the strangest features of black holes is the redshift of light escaping their gravity well. Light climbing out loses energy, stretching into longer, redder wavelengths, the gravitational redshift. This effect is faint off the edges of gravity wells but becomes vast near black holes, colouring the cosmos with stretched whispers of ancient light. These phenomena shape the ultimate limits of time dilation. Velocity can slow time, but gravity can freeze it. The black hole's edge is a boundary not just in space, but in time itself. It is a place where seconds fold into centuries and moments stretch into infinity, revealing the hidden geometry of space-time and the profound link between mass, gravity, and time. Thus, black holes are not merely cosmic monsters, they are the universe's most dramatic proof that time is malleable, a living echo of Einstein's revelation that space and time are not fixed and eternal, but fluid, intertwined, and shaped by the masses and motions that inhabit the cosmos. They remind us that while travelling near light speed bends time like rivers flowing around rocks, gravity can anchor it in deep wells, freezing moments forever at the edge of the invisible abyss. At the boundary of a black hole lies the event horizon, a point of no return where gravity grows so intense that not even light can escape. Here, time itself is twisted into something beyond ordinary comprehension. To an observer far away, a traveller falling into the black hole appears to slow and freeze at the edge, suspended in a thin sliver of time stretching indefinitely. Every second that passes for the observer feels like an eternity for the falling traveller. Inside the event horizon, time's progression bends harshly. For the traveller crossing it, seconds still tick in their own frame, but outside, years, centuries, even millennia flood past in seconds. The event horizon is the ultimate time dilation machine, where the fabric of space-time folds and the normal flow of moments fractures. The immense gravity near black holes also stretches light emerging from this region into the red and infrared spectrum, an effect called gravitational redshift. This phenomenon means that photons climbing out of the gravity well lose energy, making the black hole appear colder and darker, veiling the abyss in a shroud of slow time and fading light. Black holes illustrate the ultimate extreme cases of time dilation, where velocity-induced dilation from travelling near light speed shifts into gravity-induced dilation from mass itself warping time. They reveal how space and time are fluid, bending in response to forces both immense and subtle. These cosmic monsters stand as testaments to relativity's strange promises, that time can slow, stretch, and freeze depending on where you stand in the universe's deep architecture. The edge of a black hole is nature's theatre for this profound interplay, a boundary where the universe's oldest secrets and wildest physics meet in a dance of eternal moments. Time dilation is not just a cosmic curiosity seen in particle accelerators or black holes. It affects everyday life, including the very technology you carry in your pocket. The Global Positioning System, or GPS, relies on a network of satellites orbiting Earth at altitudes of about 20,000 kilometers. These satellites are moving faster and farther from Earth's gravitational field than you are on the surface, making their clocks tick differently. The satellite's atomic clocks, which keep incredibly precise time, run faster due to weaker gravity but slower because of their orbital velocity. The net effect is that satellite clocks tick about 38 microseconds faster per day compared to clocks on Earth's surface. Without correcting for this difference, just a fraction of a second, GPS would miscalculate positions by kilometers after only a day. Engineers built relativistic corrections into GPS algorithms from the start to account for time dilation effects predicted by Einstein's theories. These corrections synchronize satellite and ground clocks, ensuring that signals arrive with the precise timing needed to triangulate locations on Earth with meter-scale accuracy. The satellite network is a daily global experiment in relativity in action. GPS thus turns abstract physics into practical utility. The theories developed to understand the extreme, like black holes and high-speed travel, are indispensable in the mundane task of guiding your phone or car through city streets. Every map request, every navigation prompt, depends on understanding how velocity and gravity shape the flow of time. This is relativity in your hand, making global positioning seamless and reliable. Without these adjustments, the world of precision navigation would crumble. Satellite signals would become unreliable, sending travelers and automated vehicles astray. Your journey from one place to another would be measured in miles of error, all because time ticked differently up there in space than down here on Earth. This is the hidden legacy of relativity, quietly governing the flow of time beyond our senses but crucial to technology that shapes daily life. The universe bends time and space not just in distant stars or cataclysmic events, but right above your head, guiding the voyage of humanity through the globe with silent, steady precision. Reaching near light speed is far more than a matter of building a faster engine or packing more fuel. The energy demands for such acceleration rise astronomically with every fraction of increase in velocity. To boost a single kilogram of mass to half the speed of light requires about 1.1 times 10 to the power of 16 joules, roughly the energy output of a large power plant operating continuously for months. Scaling this to a spacecraft carrying crew, life support and supplies multiplies the challenge beyond current or near-future capabilities. The mass increase predicted by relativity compounds the problem. As velocity approaches light speed, your spacecraft's effective mass grows dramatically from the perspective of external observers, making further acceleration exponentially harder. The ship becomes heavier in the cosmic sense, needing more and more energy to push just a little faster, creating a steep, unyielding barrier. Engineering solutions need to contend with this energetic hurdle. Traditional chemical rockets can never come close. Nuclear propulsion pushes farther but still falls short by orders of magnitude. Concepts like antimatter engines or fusion drives are promising but remain experimental, facing daunting technical, safety and resource challenges. Accelerating to relativistic speeds also exposes the ship to extreme interstellar conditions. Cosmic dust and gas that pose little risk at sublight velocities become high-energy projectiles capable of punching through armor and damaging electronics. Shielding against this bombardment requires advanced materials and innovative engineering, adding mass and complexity. Navigation and control systems face unique obstacles. At relativistic speeds, starfields distort and shift due to aberration and Doppler effects, complicating orientation and trajectory tracking. The delay in communication signals demands high autonomy, as real-time remote control from Earth becomes impossible over interstellar distances. Thermal management also becomes critical. Accelerating into relativistic regimes generates heat from onboard systems and particle impacts. Radiating this heat away in deep space, with minimal external conduction or convection, challenges designers to develop efficient cooling strategies. Finally, the human factor cannot be ignored. Crews must withstand prolonged isolation, radiation exposure, and the psychological stresses of time dilation, living normal lifespans while loved ones age centuries apart. Life support, medical care, and mental health systems require unprecedented reliability and sophistication. In short, the soaring ambitions to cross the stars come tethered to colossal physical, technical, and human challenges. The limits of human engineering are the limits of our current understanding, materials, and energy harnessing. Overcoming these requires not just faster ships, but transformative advances across science and technology. Until then, light speed remains an ultimate frontier, illuminating how the universe's fundamental laws shape the dreams and constraints of interstellar travel. To reach speeds nearing that of light, humanity must move beyond chemical and even nuclear propulsion into realms of extraordinary energy and efficiency. Antimatter engines represent one of the most promising theoretical solutions to this challenge. When matter and antimatter meet, they annihilate each other, releasing energy with unparalleled density, far exceeding the output of conventional fuel sources. Harnessing this power could provide the thrust needed to accelerate a spacecraft to relativistic speeds. Yet building such an engine is a monumental task. Producing, storing and controlling antimatter in sufficient quantities while avoiding catastrophic energy releases remains beyond current technology. The tiniest breach in containment could release energy equivalent to multiple nuclear bombs, making the design of antimatter propulsion systems one of the most dangerous engineering challenges imaginable. Other concepts explore fusion drives that burn isotopes like deuterium and helium-3, offering high thrust with far greater efficiency than chemical rockets. Still, these rely on large supplies of rare fuels and complex containment fields, pushing the limits of materials science and reactor design. More speculative are ideas using magnetic sails, light sails powered by lasers or starlight to accelerate tiny probes without onboard fuel, or exotic drives based on hypothetical physics. Despite the challenges, continuing research into these propulsion technologies is vital if humanity hopes to become an interstellar species. Without new engines capable of harnessing immense energies safely and efficiently, journeys to distant stars will remain dreams tethered to centuries of travel time. The future engines of exploration will not just carry us across space but through time itself, unlocking the secret of practical relativistic travel and perhaps immortalizing the travelers who dare to reach for the stars. Relativity offers a gift and a curse for building a civilization that spans the stars. The gift is the ability to cross vast cosmic oceans within a lifetime aboard a relativistic starship. The curse is the divergence of time itself, making coordinated civilization across different worlds nearly impossible. With time dilation, travelers moving at near light speed experience decades while centuries or millennia pass on their homeworlds. Establishing human colonies on distant planets means settlers return to worlds fundamentally changed, their home cultures altered or even vanished. Communication delays stretch to years or centuries, making real-time cooperation or governance infeasible. This temporal fragmentation creates isolation. Each colony experiences time at its own pace relative to others, creating distinct asynchronous civilizations out of what was once a unified species. Synchronizing knowledge, decisions, and culture across these temporal gulfs becomes a monumental challenge. Moreover, the energy and engineering barriers to frequent travel or communication across such vast distances make regular contact rare or impossible. Autonomy and local self-sufficiency grow essential, but autonomy severs shared identity. Civilizations fracture along temporal and spatial lines. In other words, the dream of a galaxy-wide human civilization must grapple with the paradox of relativity. The very physics that enable near-light-speed travel also sow the seeds of cultural and temporal divergence. The future of interstellar humanity may be a mosaic of isolated enclaves, each living in its own era, connected by shared heritage but divided by the relentless flow of relativistic time. Building a true interstellar civilization requires innovative solutions, not just in propulsion and energy, but in philosophy, governance, and social cohesion. Time dilation challenges us to rethink what it means to be a civilization spread among the stars, caught in the cosmic dance where time itself plays the lead. In the vast gulf between stars, communication becomes a profound challenge. The speed of light is the universe's ultimate speed limit, not just for matter, but for information itself. When a message travels from an interstellar spacecraft to Earth, it moves at the speed of light. But with distances measured in light years, even the fastest signal takes years to arrive. A simple question back and forth could stretch into decades-long conversations, fracturing real-time dialogue into agonizingly slow exchanges. This temporal lag creates a web of complications. Commanders aboard a relativistic starship might send updates, but the replies arrive centuries later. Information that seems urgent could be outdated upon arrival, and decisions made on Earth might reach the crew after critical events have passed. This forces spacecraft autonomy to paramount importance, shifting many decisions from human controllers on Earth to artificial intelligence on board. Moreover, the nature of time dilation itself warps the perspective between sender and receiver. While the crew experiences one flow of time, Earth observes another, leading to asymmetrical aging and differing operational timelines. Coordinating activities or sharing scientific data requires accounting for these mismatched clocks, creating additional layers of complexity. Efforts to overcome these hurdles include developing new communication protocols that can handle delayed, asynchronous exchanges and designing onboard systems capable of independent operation during long silences. Advanced error correction and data compression become critical to preserve message integrity across years of transmission. The isolation deepens beyond mere delay. Psychologically, knowing that replies from Earth will arrive long after you've forgotten sending the message changes the nature of interaction. Conversations lose immediacy, community shrinks, and human connection weakens with distance and time. For crews traversing the relativistic gulf, the void is as much a barrier as the space between stars. Interstellar communication is thus not just a technical problem but a challenge of human resilience and ingenuity. It demands a reimagining of relationships, autonomy, and trust in machines to bridge the silence. The void between worlds is vast, and messages that cross it carry the weight not just of information, but of the profound loneliness and hope that accompanies every human journey into the stars. There is a harsh truth tethered to every dream of travelling near light speed. Your rocket runs on fuel, and fuel is heavy. As velocity increases, more and more energy is needed, not just linearly but exponentially, to push it just a little faster. This is the relativistic rocket problem, a brutal barrier born from the laws of physics themselves. When you accelerate a spacecraft, you burn fuel, propelling the ship forward. But as your speed approaches that of light, the mass increase predicted by relativity makes acceleration infinitely expensive in energy terms. The faster you go, the heavier you become, and the more fuel you need to accelerate further. It is a vicious cycle that demands exponentially more fuel for ever smaller gains in speed. This exponential demand grows impractical quickly. To reach even half the speed of light without time dilation tricks, a spaceship must carry so much fuel that it might never leave Earth's gravity well. And carrying fuel adds weight, which requires more fuel to move, a seemingly endless spiral that plagues any conventional propulsion concept. Engineers have proposed clever solutions, from multi-stage rockets to antimatter engines, but the fundamental physics remain unforgiving. Every kilogram of fuel saved is precious, and every gram added drags the journey down. Realistically, no spacecraft can carry enough energy and propel itself to light speed using current or near-future technologies. This challenge forces a reconsideration of how we think about space travel. Perhaps the future lies not in brute force but in elegant physics, using gravity assists, solar sails, or more speculative devices tapping cosmic phenomena. Or perhaps in transcending traditional fuel entirely, harnessing quantum effects or space-time warping to leap across the stars without the costly burden of mass and fuel. Until such breakthroughs arrive, the relativistic rocket problem stands as a reminder that the universe's laws are not obstacles to be broken, but profound truths to understand and work within. The journey to the stars is both a technical and philosophical challenge, a test of human ingenuity and humility in the face of cosmic scale and speed. When we dream of conquering interstellar distances, two ideas emerge for beating the stubborn barrier of human lifespan: suspended animation, the science fiction trope of freezing or pausing our bodies in time, and time dilation, the cold, elegant truth from physics. Both promise to stretch life across vast expanses, but they operate very differently. Suspended animation is biological stasis, a deep freeze where metabolism and biological processes slow or stop altogether. This is akin to pressing pause on life itself, hoping to restart clocks once the journey is done. While medical science has developed techniques for hypothermia and metabolic slowing, true long-term suspended animation remains beyond current capability, fraught with challenges like cellular damage and unknown effects on cognition and consciousness. Time dilation, on the other hand, leverages relativity's gift. When travelling near the speed of light, your body ages naturally, but slower relative to those left behind. You don't pause, you live fully, in real time, but the universe around you accelerates. A voyage that seems like a lifetime to you might span centuries to Earth. Time dilation grants biological immortality by letting you move through the cosmos faster than time flows outside your frame. The critical difference is agency and experience. Suspended animation freezes you in a timeless void where your subjective experience halts. Time dilation lets you age normally, experiencing moments fully, but bending the flow of time relative to others. One is a stopgap on biology, the other a structural feature of the universe. Practically, both will be essential in future space travel. Suspended animation could reduce resource loads and psychological stress on long voyages that cannot reach relativistic speeds. Time dilation will enable travellers moving near light speed to extend lifespans naturally while crossing vast star fields. Together, these approaches offer complementary tools to transcend human limits. The frozen traveller and the relativistic voyager embody different paths to immortality, one by pausing the dance, the other by changing its tempo. Both remind us that time is not only a relentless flow, but a manipulable dimension, waiting for humanity to master in the voyage beyond stars. From the comfort of your fast-moving starship, the universe looks completely different. Relativity lets you shrink vast distances and race through star fields, but the cosmos still has a horizon, a limit beyond which you cannot see or reach. This is the edge of the observable universe, a boundary not in space but in time itself. Beyond it lies regions so distant that light from them has not yet reached us. Even travelling near light speed, these areas remain forever out of reach. This cosmic horizon defines the limits of your journey. You might cross galaxies, travel between stars and age slowly while centuries pass by outside your window. But there are places the speed of light forbids you to touch. The observable universe is a living archive of the cosmos's past, but it is not infinite in your view. Like a ship navigating a vast sea, you face the horizon where light, carrying the stories of distant stars and ancient galaxies, has not yet arrived. Beyond this line, you enter the unknown. Looking back, this horizon shifts with your journey. As you speed away, the light from distant galaxies becomes ever fainter, red-shifted beyond recognition. Their stories slip into silence, their images fade into cosmic dusk. The boundary of what you can observe contracts, shaped by your velocity and the flow of time. This edge is more than a limit. It is a filter that shapes the reality of interstellar travel. The universe you explore is framed by light's arrival. Whatever lies beyond the horizon is a mystery unseen and perhaps unreachable. This boundary reminds you that no matter how fast you go, you cannot escape the fundamental interplay between space, time, and light, the cosmic dance that defines existence. Understanding the horizon also shapes how we think about our place in the universe. It marks not just the limit of our vision, but the dynamic boundary of reality, as experienced by any traveller moving through space-time. Travelling at relativistic speeds lets you push these boundaries, but the universe always preserves a frontier beyond your reach, a silent testament to the vastness yet to be explored and the eternal nature of cosmic time. At the frontier of physics, where quantum mechanics brushes against relativity, new mysteries emerge, tiny ripples in space-time that blur the lines between certainty and probability. Imagine the quantum world as a seething ocean beneath the calm surface of classical reality. Waves overlapping and interfering, not just particles moving, but possibilities unfolding. Recent theoretical work suggests that gravitational waves, the ripples caused by colliding black holes or merging neutron stars, may carry quantum signatures. These quantum gravitational waves might entangle distant parts of space-time, creating correlations and quantum shadows that classical physics cannot explain. Though ordinary gravitational waves behave as Einstein predicted, these quantum imprints offer a glimpse of an underlying microscopic quantum structure of the cosmos. This tantalizing interplay could open new doors in space travel. Quantum effects in relativistic engines or propulsion systems might someday enable efficient momentum exchange with the quantum vacuum, the restless background field that permeates all space. Concepts like the relativistic motor imagine harnessing quantum electromagnetic fields to generate thrust without traditional propellant, potentially unlocking a new era of propulsion where space-time itself pushes the ship forward. But these ideas remain speculative, unfolding at the edge of theory. Integrating quantum mechanics and relativity continues to challenge physicists as they seek a unified framework that explains particles, forces, and space-time at all scales. The completion of this grand synthesis could rewrite everything we know about motion, energy, and time, even revealing new pathways to surmount the light-speed barrier. For now, the quantum whispers echo faintly behind the roar of relativity's engines. They hint that the universe's ultimate secret may lie in reconciling the smooth cosmic dance of gravity with the jittery quantum steps of matter, and perhaps, in this union, humanity will find the key to truly mastering time, space, and the epic journey to immortality among the stars. Quantum entanglement, a phenomenon once dubbed spooky action at a distance by Einstein, is emerging as a game-changer in space exploration technology. Entangled particles share a connection so profound that the state of one instantly influences the other, no matter the distance between them. This property is being harnessed for new forms of communication, sensing, and computation, promising transformative advances for spacecraft and interstellar travel. Space experiments such as the SEEK project aboard the International Space Station are pioneering space-based quantum communication. By generating and detecting entangled photons in space, they test technologies for quantum networks that can stretch across vast cosmic distances with unmatched security and speed. The goal is to build quantum cloud computing and instant communication between spacecraft and Earth, overcoming the traditional delays imposed by light-speed signals. Though quantum entanglement cannot transmit information faster than light, it provides ultra-secure communication channels resistant to eavesdropping and interference, an essential feature for sensitive command and control of distant missions. Advances in quantum teleportation also offer methods to transfer quantum states, underpinning future quantum computing capabilities on board spacecraft. Looking ahead, Quantum engines powered by entanglement are a tantalizing concept attracting research interest. These theoretical engines could exploit non-local quantum correlations to convert energy more efficiently or to tap into exotic quantum vacuum effects for propulsion. While still speculative and in early research phases, these ideas may redefine how we move through space and time. Quantum entanglement also underlies advanced quantum sensors, capable of detecting gravitational waves, magnetic fields, and time with unprecedented precision. Such sensors improve navigation, help characterize distant cosmic structures, and potentially enable new propulsion methods by manipulating quantum fields. The integration of relativity and quantum mechanics remains a frontier challenge of physics. Resolving their interplay promises to unlock the ultimate secrets of space-time, enabling humanity's leap beyond the classical limits that bind current technologies. In sum, quantum entanglement propels space travel into a new dimension, ushering in secure communication networks, advanced sensing, and perhaps quantum propulsion systems that together will carry humanity on journeys across the fabric of the cosmos and time itself. Quantum computing promises to revolutionize space exploration in ways classical computers never could. Its unparalleled ability to process massive datasets and solve intricate optimization problems in parallel makes it uniquely suited for the challenges of deep space missions. As spacecraft venture farther and missions grow more complex, quantum processors will become essential tools for navigation, data analysis, and autonomous decision-making. Picture a spacecraft journeying across the stars, facing an unpredictable cosmos filled with cosmic rays, micrometeoroids, and the chaotic dance of gravitational fields. Quantum computing's speed and efficiency enable real-time processing of sensor data, anomaly detection, and course correction, all without waiting for delayed instructions from Earth. This autonomy is crucial where communication lags stretch to hours, days, or years. Quantum algorithms excel at trajectory optimization, analyzing millions of potential routes rapidly to find paths that maximize fuel efficiency, minimize time, or adapt dynamically to changing environments. By leveraging quantum-enhanced machine learning, spacecraft can adapt onboard experiments, calibrate instruments, and manage resources with unprecedented precision. NASA's Quantum Artificial Intelligence Lab and collaborations with industry pioneers are already pushing the frontier, running quantum classical hybrid algorithms on space-related problems. From planning Earth-Mars transfers to optimizing satellite constellations, quantum computing is transcending theory and forging practical aerospace applications. One remarkable development is the deployment of compact quantum hardware in orbit, demonstrating quantum systems can endure harsh space conditions and operate at scale. These advances signal a future where onboard quantum processors guide missions through deep space and even support interstellar exploration. Beyond navigation, quantum computing could illuminate the universe's deepest mysteries by processing the astronomical datasets pouring in from observatories and space telescopes. Detecting unknown signals, mapping cosmic structures, and testing fundamental physics may all rely on quantum-enhanced computation. In essence, quantum computing does not merely promise faster calculations, but a new way of thinking and operating in space. It transforms spacecraft from remote extensions of Earth control into intelligent, adaptive explorers, capable of mastering the complex, relativistic, and quantum environment of the cosmos. The quantum age of space navigation and exploration is arriving, not as science fiction, but as a tangible evolution in how humanity journeys beyond the stars, weaving together quantum mysteries with cosmic voyages into a future where time, space, and information flow with unparalleled harmony.